So let's look next at the confidence interval where we don't know sigma. So how do we get the margin of error there? And I'm going to basically just kind of cut and paste this because we'll use the same format really. It's so similar, you know. We'll do formulas. Okay, so I'll just change this to confidence instead of P. Okay, so it starts off the same way actually. It turns out that the formula for the confidence interval, again, is x bar plus or minus the margin of error. X bar, the same sort of thing. It's either going to be given or we're going to have to compute it from scratch. Okay. So let me bring this all the way over. There we go. Okay, so let me bring that in a little bit. So, you know, x bar again, you know, we're either going to know this, it's going to be given, or we're just going to compute it, so that's easy. The margin of error has the same basic form. Notice that it's going to be the critical value times the standard deviation of x bar. But actually, the standard deviation of x bar has to be estimated. So we're going to put here something a little bit different. We're going to put estimated standard deviation of x bar. Okay. And how are we going to get this? Well, the estimated standard deviation of x bar, we don't know what sigma is, right? So it has to be the sample standard deviation. So instead of the population, this is now going to be S, the sample standard deviation, divided by the square root of n. This is not known by the central limit theorem, but there is a theorem that's closely related to the central limit theorem that allows you to prove this. So I have to change a few things, okay? So this is going to be my sample standard deviation, and then this will be the estimated. Okay? So these guys will all go together. Okay. So this is the formula that we've seen a lot. So notice that when we're calculating the estimated standard deviation of x bar, the formula is basically the same, except now I don't know sigma, the population standard deviation, so I just swap S for sigma. Okay? Now, the part with alpha and the critical value and everything is also very, very similar. So notice that we need this critical value. The margin of error is still a product of the critical value times something that's the standard deviation of x bar, whether it's the exact or estimated. So we're going to start off with a critical value, getting alpha the same way. We're going to figure out what the confidence is. Of course, that's going to be given to us when they tell us what sort of confidence interval we want. We're going to subtract 1 from that and get alpha. But now we have to be careful because the critical value is no longer going to be the z-score. It's going to be the t-score. Okay? And we have to be careful when we compute this critical value because it's going to be equal to t dot inv of alpha divided by 2. And I'm going to need my degrees of freedom. And that's going to be equal to n minus 1. Okay? And so now we go ahead, we do the same thing. We compute the margin of error like before, subtract it from x bar, add it to x bar to get the margin of error. And we end up with our final confidence interval. So notice how similar it is. All we do is we swap sigma for S, and we swap the z-score for a t-score. It's actually very, very easy. We could actually rework the last problem if we wanted to, but let me go ahead and work one from the book. But I could actually work the problem from. Okay, so let's see. I have a problem from the book here. I got, let's say, 8.15. Okay. So it says a marketing researcher wants to estimate the mean savings. Okay, so that's telling me automatically I'm going to be looking at mu realized by shoppers in the showroom. Showrooming is the practice of inspecting products in retail stores and then purchasing the products online at a lower price. Okay, so This guy wants to figure out how much he's losing, the average amount of money he's losing per customer. Okay, so this first part's important. A random sample of 100 shoppers who recently purchased a consumer electronic item online after making a visit to a retail store yielded a mean savings of $58 and a standard deviation of 55. Okay, so the first thing I want to notice is that both the mean and the standard deviation relate to the sample. Okay, so we have a sample size of 100. The mean amount that they saved was 58. The standard deviation was 55. So now I can compute the estimated standard deviation of x bar. It's just going to be standard deviation of x, the sample standard deviation of x, divided by the square root of n. Of course, square root of 100 is 10, but I'll compute it out. Okay. And we're going to get 3.3. Okay, so let's go and construct a 95% confidence interval. So I'm going to write the confidence as a decimal place. And I'm going to go ahead and compute alpha as 1 minus the confidence. So alpha plus the confidence has to equal 100%. Okay, now I want the critical value. So what I really want here is I want the t-score for the alpha over 2 percentile. Okay, so I have to use t.inv. I'm going from a percentile to a t-score. So this is alpha divided by 2. My degrees of freedom are n minus 1. So I'm going to hit this minus 1. And that's my critical value. And again, I'm going to make it positive. You could just put a negative or use the absolute value. And I'll end up getting this. And now I'm ready for the margin of error. Okay, so the margin of error is just equal to estimated standard deviation of x bar times the critical value. Okay, and then we'll just round these off real quick. We don't want that many decimal places. Okay. Now I'm going to get the lower endpoint. The lower endpoint says take whatever x bar is and subtract the margin of error from it. And I'm just going to cut and paste that. Notice that I'm dealing in money, so I can round this off to 2 decimal places. Probably not a bad idea to round everyone off because these values are in terms of money. Okay. And so now I have the 99%, I have the 95% confidence interval. I didn't change it from the last problem. 95% confidence interval for the mean. That's just equal to 51.45 to $64.55. Okay. So what he's saying is, let's think about what this means. This means that we think the true amount of money, well, let me put it another way. We think that the average amount of money a customer saves is between 51.45 and 64.55. Okay? So that answers part A. Part B is kind of interesting. It says, suppose the owners of a consumer electronic retailer wants to estimate the total value of lost sales attributed to the next 1,000 showroomers that enter their retail stores. How are the results useful? Well, if this is what we believe is the smallest amount of money that the consumer can save and the most he can save, okay, then this means that if we multiply this by 1,000, okay, we think that on average the store is going to lose between $5,140 and $6,455. Okay, so I'm going to multiply these by 100 because this is where we believe the average amount per customer is. So I multiply that by 1,000, and that tells me that the amount they're going to lose, since this is the amount the customer is saving, it's the amount the retailer loses, is between this and this. So to answer part B, We're going to multiply this by 1,000 because this is the amount per customer. So for 1,000 customers, this will be 5,144 to 6,455. So this is the amount of money. This is where we believe, we're 95% confident that for the next 1,000 people that showroom, the average amount lost is going to be between 5,144 and 6,455. Okay, I think that pretty much wraps it up for hypothesis tests.